Good. Tim passed away about 3.5 years ago, somewhat unexpectedly, leaving a big hole in my heart, as well as in an academic setting. Tim taught me how to do astrochemistry. Daniel Crawford taught me how to do theoretical chemistry when I was a PhD student at Virginia Tech. But Tim really taught me how to take quantum chemistry and apply it to molecules of astronomical and astrophysical significance. We were all young once. This is a picture of Tim, his first week in graduate school at UC Berkeley. And then this is a picture later. He did his PhD with Fritz Schaefer. At one point in time, my PhD advisor, my postdoctoral advisor, and my department chair all did their PhDs with Fritz Schaefer. So the theoretical chemistry world goes through there. But in this picture, we have Tim here in the middle, and then that's his wife, Julia Rice. They met when they were, she was a visiting scholar, and then he was a graduate student. Then he went to Cambridge because she's from the UK. And then if anybody knows Wesley Allen, he came between them in this photograph. This is how I knew Tim. Tim had the same uniform. He wore it every day. He was a classic baby boomer. White New Balance tennis shoes. Cargo shorts. White socks up to the knee. Collared shirt. Berkeley sweatshirt over top of it. Every day, every time I knew him. But I always knew that Tim was having, and I love this picture because I always knew that Tim was having a good time, or he found somebody incredibly stupid when he had the same look on his face. Whenever he caught somebody in NASA administration being a total jerk, he would go, and that's always the look that he would give. This is the only picture that Tim and I have together. As you can tell, I was much younger then and had slightly more hair. But this is the only picture that Tim and I took together. I was a graduate student then, went to visit him out at NASA Ames. And one of my great regrets in life is that we didn't make more, I didn't take more pictures, didn't have more memories together. But Tim and I published over 50 papers together. And he was a huge influence in my life. And so the thing that I want to give to each and every one of you, you know, we have mentors in our lives. We have undergraduate advisors, we have graduate advisors, we have postdoctoral advisors. When you become a faculty member, you have older faculty that try to take care of you. You have mentors in your life. And as we get older, they pass on. And what I have found is like your mentors are kind of like a piece of armor. They protect you, they help you. And then when they're gone, it's like that piece of armor is no longer there. And you have to fight for that. But we can honor their memory and their legacy by remembering where they used to be in our suit of armor, and then making that a strength and forging ahead into the battle against ignorance. All right, so Tim really taught me how to love space. And this is one of the things that I love about astrochemistry. I get to show pictures like this. We get to cheat because these are just mind-boggling images. So in this photograph are actually an overlay of two different telescopes. So in the foreground, we have a dust image that we get from the James Webb Space Telescope. And in the background, we have an X-ray image from the Chandra X-ray Observatory. And it shows that different wavelengths of light are giving different pieces of information. They're implying that we have fundamentally different chemistry at different wavelengths of light. Because we have the dust in the foreground, and in the back, we have this wealth of stars. And so what we are able to do as astrochemists is to probe what the molecules are in these regions in order to see how the physics of those regions affects them. This is called the Tarantula Nebula, because if you squint and look hard, you know, if you've ever, you wouldn't see these in Miami because there's too much light pollution, and there's also too much humidity in the atmosphere. But if you ever go somewhere where it's dry and cold, and you look up in the stars, you see some of the constellations. You look at Orion, and you're like, yeah, that kind of looks like a dude beating an animal over the head with a club. And then you look at Scorpio, and you're like, yeah, I can see the tail of the scorpion. And then you see 3 stars and a W, and you're like, that does not look like a princess. Cassiopeia is a little different. But if you squint here, you might be able to see a tarantula emerging out from underneath the dust. Another picture that I like to show is this one. This is a very special type of star called a Wolf-Rayet star. These have very weird, from a nucleophysics standpoint, these have a very weird evolution. You get strange elements that come out of this. So one of the things that I like about Wolf-Rayet stars is that they have a tendency to overproduce fluorine. they have a tendency to overproduce aluminum. And aluminum has become an element near and dear to my heart. No offense to any organic chemists in the room. I am not going to stand up here and show you a black and white screen with synthetic pathways that have percentages over each of the arrows. I know that's important. I'm just not going to do it that way. All right, so what are we going to do? In astrochemistry, we have this thing called the astrochemist's periodic table. The size of the box is proportionate to the amount of material that the universe is made of. The universe is 99% hydrogen and helium. It's been nice talking to you. I'll go back to the airport now. Okay, if we get rid of the hydrogen and helium and you squint really hard, you'll see these little teeny tiny boxes made up of other elements. So let's get rid of the hydrogen and the helium because they're just big and obnoxious anyway. And if we look at the elemental abundance of the universe, it looks something like this. Most of the universe is not really carbon. Now, carbon's a big wedge. Carbon's a big wedge. Most of the carbon in the universe is tied up in one molecule. Anybody guess? Close. Take off the two. Carbon monoxide. Most of the carbon in the universe is tied up in carbon monoxide. Okay, so let's do a little chemistry. If we have this wedge and we overlay that wedge onto this wedge, it's right here, which means that we have more oxygen left to do some chemistry. But why is it that astrochemists are addicted to carbon? For the same reason that all chemists are addicted to carbon. Because it just does things. It does all interesting things. You know, it's like that really popular person at the party that everybody wants to talk to. And all the rest of us, because we're scientists, we don't have social skills. So we're all standing on the other side just wishing we could talk to that other person. But we don't. Carbon's the cool kid. But carbon's not the most abundant thing. Can we do something else? Yes. Otherwise, I wouldn't be here talking to you today. This is the universe writ large. Let's take that to a smaller region of the universe. And let's look at a different elemental abundance. This is the elemental abundance of something that we all love and should cherish, that we should all take care of, and we should all appreciate. What is that?
Earth.
That's the elemental abundance of the Earth's mantle. Oh. And most of it, this thing is going to kill me. Most of it is oxygen. And then we have some magnesium and some silicon. They're kind of 50-50. Then we've got some other things floating around in the Earth. But if we look at the crust, it's a little different. There's about 4% carbon. But most of the Earth is oxygen. There's some interesting chemistry with that. Had a young man. This will make you feel bad about yourself. Had a young man who was in high school. He was a junior in high school. And he comes up to me one day and he says, Dr. Fortenberry, I hear you do computational chemistry. Said, yeah. He said, I would like to do some work with you. Okay. So I thought about a project for this. I said, I got to keep this precocious kid entertained for a couple of months. I said, Edmund, this is terrible. I want you to calculate the bond energy for a single bond between every element in the first three rows of the periodic table and every other element on the first three rows of the periodic table. I was gracious and said he didn't have to do the noble gases. That's a different project and a different talk for another time. Josh and I were commiserating about that a few minutes ago. You know the thing about this? 5 weeks later, he gave me this table. He had calculated the whole thing, and he did it on nights and weekends when he wasn't at robotics practice or learning his third language or figuring out how to code in COBOL because it was cool and his dad told him he should do this. He did it in 5 weeks. So he calculated the bond strength for all of these things. Okay, and he went to the University of Pennsylvania and he's now doing a PhD, I think, at Stanford. So, he's an overachievement. His dad also happened to be a quantum chemist as well. But some interesting things came out of this. Some really interesting things came out of this. If you look at it, if you look at the bond strengths, you can see periodic trends. But something happened that I did not expect, and this is kind of a side story. The strongest bond, single bond, not talking about double bonds or multiple bonds or sharing pi electrons, the strongest bond, single bond on the periodic table is between beryllium and fluorine. Second strongest bond is between boron and fluorine. It just so happens that the three least abundant elements on the periodic table, where you get to iron, are beryllium, boron, and fluorine. This is a good thing for us. They form really, really strong bonds. They don't really polymerize. Beryllium is a teratogen because it rips everything apart that it touches. Fluorine, we talk about hydrofluoric acid. This is nasty stuff. If you've ever met a fluorine chemist, don't ask them to give you a high five because they might give you a high two. So these are nasty things. And it just so happens that they are depleted in the universe as we know it, which is fortunate. Anyway, I find that fascinating. The other thing that I came across was a gulf of stability. We talk about this in nuclear structure, but this gulf of stability, where we have really, really strong bonds in the middle of the diagram. Oxygen forms really strong bonds to things on the other side of the periodic table, the strongest of which is aluminum oxide. Inorganic chemists have known this for a while. Aluminum and oxygen form really strong bonds. The other thing that's weird about aluminum and oxygen bonds is while they are very strong, they're actually really, really loose. So the molecule that we were using to calculate this, I'll show you in a minute. But the molecule that we use to calculate this has a free OH rotation that it flies around. But here's the thing that I thought was cool. These are some of the strongest bonds on the periodic table. Oxygen, silicon, magnesium. Oxygen, silicon, magnesium. And there's even some aluminum. Aluminum is depleted in general because it's not a very stable nucleus. So it just so happens that there's a coincidence between bond strength and elemental abundance in minerals that we get. And I was fortunate to have a high school student's first research paper made it to the cover of the journal.
That's wild.
Yeah, I know. So the molecule that we're looking at is this one. It's this weird little alcohol. And it has this nearly free rotation of this OH. When I think about this nearly free rotation, I actually think about it kind of like your shoulder, because hopefully it's pretty tightly connected to your body, but it can wee really fast around. And so it's a similar type of joint that you create. I saw this molecule, I said, oh, this is crazy. I've never seen this before. If you think, so here's a piece of advice for all the students in the room especially. If you think you have a brand new idea to science, you don't. Somebody probably did it 50 years ago, but not all hope is lost, because you can hope that the technology has advanced to a point where now you have something unique and interesting to say. I was fortunate, so I dug through the literature, always go back to the literature and always make sure that nobody has done this before or they haven't done it the way that you think they have. I was fortunate to come across this reaction, and this was the only one that I could find that involved this particular molecule, because here it is, the product at the end. This was published in 2009. I stopped dead in my tracks when I saw this. This was originally done as a means of producing hydrogen, H2 for alternative fuels. When I saw it, I said, that is perfect. In astrochemistry, we're in the gas phase. We're not getting any extra energy. At most, we'll get two things to collide, but we're not going to get anything more than that. And by things, I mean photons, I mean particles, I mean any, you get two. 1, 2. And we need it to be thermodynamic. We need it to be thermodynamically favorable. We need the energy of our transition state to be submerged, because we're not going to climb that hill because we don't have any other source of energy. And we need a leaving group to take away that excess energy that we gain. Sabrina and I were talking about this morning. Who likes to go skiing? I know this is something you do all the time in Miami. Who likes to ride roller coasters? This is Florida. Yeah, okay. This is Florida. You go to Universal Studios. You go to Universal Studios, you ride the Velocicoaster. My kids love it, especially when the Velociraptor jumps out at you at the bottom of it, and then my wife screams louder than any of the kids do. What is the highest point you're going to be on this entire roller coaster?
Beginning.
At the very beginning, you go click, 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 click. And if you're riding with my wife, she's going to go, this isn't safe, this isn't safe. Why did you make me do this? I hate you, I hate you, I hate you. And then we get to the end. That was great. Can we do it again? But the highest point you're going to be is at the very beginning. Why? Why can't you go higher? Oh, by the way, when I got here yesterday, apparently Creed is playing on a cruise ship. And there were like 500 middle-aged Creed fans all over the place. So anyway, I was just thinking, can you take me high? All right, so we're up here at the very top. Why can you not come back up again? You don't have enough energy. Why can't you even come back up to where you started? Friction, yes, friction. The friction slows you down. Same thing is true in quantum chemistry. It's not friction in the same sense. You're giving off vibrational photons as you're vibrationally descending. So we have a roller coaster ride that's thermodynamically favorable. We have a submerged barrier so that we can get to the next part. So we're at the top of the velocicoaster. We come back up not quite as high, but then we can keep the reaction going. And then we have a leaving group that's going to take away that kinetic energy. And what's the leaving group? It's H2. What's the most common molecule in the universe? H2. Effectively, the entire universe is a low-density solution where H2 is the solvent, and the Earth is an aggregated particle in the middle of the solvent. We're making H2. We're doing all the things that we need to do to have interesting gas-phase chemistry, and we're making an aluminum-oxygen bond. So I said, they've done this before. This is really exciting. I recreated it with a slightly higher level of theory. And then I said, and then I did that thing that y'all never do. I became obsessed with this reaction. And I spent an entire summer doing this because what happened next was fascinating. I kept adding water and ALH3, and it cascaded down, and it kept happening. I could add a water, I could add an alane. The energy was never higher in the transition state than it had been in the previous reaction pathway, and it kept going on, and I went to the point where my computations were too big, and that's when I had to stop. But it was one of the luckiest things that ever happened to me when I stopped, because I stopped down here. Okay, let me make that bigger. Sweet, all right, there we go. So let's ignore the H6 on the outside because it's going to decorate the periphery. Some of y'all TA Gen Chem, some of y'all teach Gen Chem, all of y'all took Gen Chem. So we're talking about ionic bonding. What do? We say, well, this one, Al2O3 is the classic example because you have a charge on the aluminum of +3, and then you have a charge of -2. And some of my students taught me this the other day. You swap and drop. And those of you that are fans of wrestling. So we swap and drop. Better not do that again. And we make Al2O3. It's the classic example. It's a classic ionic compound. But it's also a common thing in the earth. Al2O3 makes the mineral corundum. This is a photograph that I took of a corundum. Speaking of Canada, see, there we go. This is from Canada too. So if we have corundum, it's this gray rock. Not very exciting, not very appealing, but it is a mineral that's known. Apparently, if you take corundum and you put in a teeny tiny little bit of chromium, it makes ruby. So the title of this paper was Gas Phase Creation of the Smallest Ruby, where we had our roller coaster ski downhill reaction that eventually leads to a cluster that has the same empirical form of these larger things. I believe that we could continue to add water, we could continue to add ALH3 onto those molecules and have this process continue. That's great. The question is, theory is wonderful. Theory allows you to do anything you want. The problem is theory allows you to do anything you want. We need some tangible evidence to be able to detect these molecules. My bread and butter actually comes from spectroscopic characterization of molecules for observation in space. If we want to be able to observe this molecule, we need some information about its spectrum. We need either some vibrations or some rotations, preferably both. We have this beautiful thing called the James Webb Space Telescope. Yes, I made my children watch the launch of the James Webb Space Telescope on Christmas Day. They weren't watching it, they were playing with their toys. I was watching it. So we have this telescope. Can we find some vibrational frequencies that would allow for its detection? If we look at JWST, it has two main instruments that we want. The near spec, NASA got really creative with this one. You want to know what near spec stands for? Near infrared spectrometer. Yeah. And then we have MIRI over here. Anybody know what that one is? Mid infrared instrument. Got to make it a little different.
Oh.
And it has, and MIRI has a range that it can observe between 2,000 wave numbers. And it says it can go all the way to 30 microns, but it's really more like 25 microns. So can we get some vibrational frequencies for this molecule? I'm a quantum chemist. I have to show you a big scary equation, right? We're obligated to show big scary equations at least once. So this is the Watson-Hamiltonian vibration rotation interaction terms that we get here. Those of you that remember your quantum, you remember what the kinetic energy operator basically is?
Oh.
Yeah. Yeah, I know what it is. Can you tell me? No. I'm going to do that. The second derivative. So we have our second derivative term. Then we have vibration, rotation, interaction pieces, as well as vibration, diagonal pieces. But the thing that we spend most of our time computing is the V on the end. That's our potential. And we calculate it as a fourth order Taylor series. So the thing that you remember from sequence, the thing that you remember so much, Taylor series, Maclaurin series. Yeah, you use it all the time. Yeah, thank you, Ashley. We got it. We use these all the time. So the practical way that we do this is we're going to start with the geometry optimization at a high level. We're going to generate some points. We're going to calculate some energies. We're going to fit those from the least squared means. We transform the coordinates. We get vibrational rotation. We get vibrational and rotational information from this. If you want to know how this works, I would love to talk to you about that. So as an example of what we do, so this is from something that, from what I understand, you'll be hearing about next fall. We've been able to do this with polycyclic aromatic hydrocarbons, where we have an experimental spectrum on the top, and then we have a traditional method on the bottom. It does everything fairly well, but then it kind of messes up around 2300 wave numbers. We can play some games with how we do this through what's called a hybrid method, and we eventually produce a spectrum for the CM stretch here that's almost exactly coincident with that experiment. So our methods that we're using are very accurate for the prediction of IR spectrum. Okay, so let's go back to these inorganic oxides. This guy has a dipole moment of 1.2 Debye. Okay, well, that's okay. It is rotationally active, not as high as I thought it would be. But we calculated a bunch of vibrational frequencies. So quantum chemists, organic chemists have to show you black and white slides and things, or quantum chemists have to show you big scary equations and giant tables of numbers that you will never be able to parse. So let me tell you what's important. Intensities are important. Here we get some, they're about 260 and 218. That means nothing. Let me give you a candle. The antisymmetric stretch in water. The thing that makes the afternoons in Miami so sweltering. Don't worry, it's true in Mississippi. Oh, it's true in Mississippi too. The thing that makes the atmosphere impossible to penetrate with infrared telescopes. The antisymmetric stretch in water is only 70 kilometers per mole in these same units. So we're 2, 3, 4 times higher. So what's happening in these regions? Why does it do this? Well, if we have this particular vibrational mode where we have the atoms vibrating, we get these huge intensities. It lights up like the sun. But if you get it, say it. Beer's law. Beer's law. If you have I equals EBC. So if you have a really, really big E, there's that other term. What is it? Think.
Thinking idea.
What's another word for thinking?
Contemplate.
What?
Contemplate.
Almost.
Concentrate.
Concentrate, yes. Concentration.
Oh, concentration.
So, Beer's law, if you have a large E, then your concentration can be small, and you still get a detectable signal. And thankfully, these molecules have these huge intensities. Let's see if this bears out. All right, so we've looked at this for this one alcohol. let's go back to this intermediate. What does it look like? This is wild stuff. So this was done by my student, Allie. She's now a graduate student at the University of Utah. She was an undergraduate in my group. Somebody tell me what's wrong with that structure.
Oh, the boys.
What molecule all the way on the left?
Yeah.
Water.
Yeah.
It's water. It's not an alcohol. It's water. Yeah.
Very confused.
Yes. Good. All right. Good. You're supposed to be confused because now I can be your savior and pull you. You would think that it would just the things wouldn't bond, but remember we have ALH3. Where does Al fall in the periodic table? You have it memorized. I know. It's right underneath boron. And nobody here is a boron because you're all smart. So if we go right underneath boron, remember boron from general chemistry? Its hybridization is sp2. It's triangular, planar, because it's missing electrons to go in that p orbital. Aluminum does the same thing. Water has 2 lone pairs. Aluminum, I need some electrons. The 2 electrons from the water donate into the empty lone pair, creating a dative bond. Some people call it a coordinated covalent bond, but it creates a dative bond. And if we go back, you'll see again it has a minimum. This is the key. This is why that intermediate goes down. This is why that transition state that makes H2 is submerged. So I had Allie calculate this. Guess what the dipole moment is going to be? Massive. So now we have a massive dipole moment, which means it's more available for rotational spectroscopy to observe. And then we've calculated, Allie calculated all the vibrational transitions, and they come in a couple of groups. The one there, nu 5, is really exciting for me because another standard candle that we have, so we have the antisymmetric stretch in water. We also have the antisymmetric stretch in carbon dioxide. And the antisymmetric stretch of carbon dioxide, the thing that we talk about climate change and global warming and such things, that antisymmetric stretch intensity, and what makes it so potent, is that it's 400. So now we have intensities that are almost the same as the antisymmetric stretch in carbon dioxide. Again, Beer's law, low concentration, we still might be able to see this, even if it's transient in nature. So then I said, all right, well, we're not always going to have water in alane. We're not always going to have water in ALH3. So I had these 2. Rebecca on the left is now a graduate student with me. She just got her GRFP. And then Kaylee on the right is probably the smartest person I've ever met. She was an undergraduate student that worked with me. She took my final exam in PChem. You gotta watch out for these things. She took my final exam in PChem, the ACS final exam in PChem. And just for fun, just for fun, she went home and from memory wrote out the entire final exam. All 120 questions, all of the possible answers. And I said, Kaylee, did you sell it? She said, no, that would be unethical. I gave it away for free. She didn't tell me that. Oh no, now you've got me worried. But she's the only other person I've ever heard about who could do this was Mozart. So the story about Mozart, when he was 12 years old, he was singing in the choir, and the Pope came to listen to the choir, and they sang a cantata that was like an hour and a half long. And the Pope said, it's so beautiful, no one else should ever be able to listen to this. And so what did Mozart do as a 12-year-old? He went home, wrote down the whole thing from memory, and then sold it on the black market. Similar type of thing. You're like, Kaylee, this is insane. Anyway, so Kaylee worked on this with Rebecca. And so we're doing ALH3 plus hydroxyl, because you're not always going to have water. And it goes through a series of reaction steps. We go downhill. And as you'll see, it has this nice formation. We have to do a hydrogen transfer to make the water molecule up here. But then when we have the water up here, these two come together in this weird little transition state. And then we can make H2 again in that process. We make this intermediate. It can rearrange, it can isomerize if it needs to. Then we hit it again with another water. It goes on to make this other structure again with that similar H2 in the middle. There is a higher energy pathway that can happen where we have to rearrange the hydrogen, but that's probably not going to happen after the hydrogen lost from the first time. But if we get this final product, it eventually goes on to make aluminum hydroxide. It's a well-known industrial. So we can create this in the gas phase. But then I said, all right, we're probably not going to have ALH3 in space. We've never found it. Famously have never found it. Can we do something else? Can we try ALH2 And if we add that to water, it just inserts into the same chemical. All right, cool. And then I had to have that uncomfortable conversation with myself. Ryan, you want to do this in space. Aluminum is not going to bond 2 hydrogens. It's probably not going to bond 3. Okay. All this fun, beautiful science, all this fun, beautiful chemistry. Nothing. All right, Rebecca, let's do it. Let's just do the reactions for ALH. Before I get to that, aluminum and oxygen, ALH2 is not known in space, but ALO is known in space. And I like to refer to this as my British molecule, because whenever you meet someone from the UK, they always go, hello. So we have AL. I have no shame. All right. This was found in 2009, I think, by Lucy Series and her group at the University of Arizona. And then this group down here was trying to come up with reaction pathways for the formation of this. So if we start all the way on the right, so we're gonna be like Eastern cultures and read from right to left. So if we start all the way on the right, we have aluminum plus water. That makes sense. It's 2 things that you should bring together. But if you want to make ALO, then you have to go through a transition state. There's not enough energy to do it. Okay, I got an idea. Let's get what we ultimately want and just put a hydrogen on it, pull the hydrogen off. Well, that has to go through a transition state, or maybe it goes through here. And while this is an energetically favorable pathway, you have to start with something that we actually don't know how it works. All right, Rebecca, I need you to do the calculation for me. So we started with ALH. And I was encouraged because I dug through the literature and I found things that previous scientists had found. ALH has actually been found in a star. It's the star. There's this little tiny red dot right there inside of the red circle. Yeah, I know. If anybody can tell me what this star system is, I will give you a double high five and do a cartwheel.
Okay, Alpha Centauri. Centauri.
Centauri.
This is the Centauri system, star system closest to us.
Yes.
And this is Proxima Centauri. So we have Alpha Centauri A, Alpha Centauri B, and that is Proxima Centauri. And ALH has been observed in the atmosphere of Proxima Centauri. So this is an astronomical molecule. I would love to say that we planned that because I just wanted to do a cartwheel, but no, that was
Here in your paper.
See, this is why you read the literature, everybody.
No, I didn't. I didn't.
Oh,
I didn't.
All right, so I said, all right, Rebecca, let's do this as simple as possible. What are the simplest things we can do? ALH is a known molecule in some astronomical contexts. Let's react with hydroxyl, forms the same intermediate that we made previously. It can bring those 2 hydrogens together in the same motif, and then we make ALO. And no one had ever explored this before. I'm like, why? Well, because they didn't think ALH was possible. I said, all right, Rebecca, let's see if we can do this with water, because water is actually more abundant than hydroxyl in most places, because hydrogen is everywhere. Ooh, intermediate, not so good. Transition state's too high. So then if we want to make ALOH, we can't do that. Oh, this stinks. Okay. Then Rebecca said, well, we've already made ALO. This is why you listen to your students. Well, we've already made ALO. What happens if I react ALO with ALH? Oh, okay. Well, quantum chemistry, you can do anything you want. Nobody's going to die. So she put them together. And we get a transition state that's somewhat submerged, and we go on to make ALOH. She showed me this. I said, Rebecca. She said, what? I said, Rebecca, what? I said, why are you putting the 2 aluminums together? What's the strongest bond on the periodic table? Oh, that's right. And so then when she flipped it around, it actually goes down here. It makes this transition state, makes this really cool intermediate. and then it loses an aluminum and makes Al. So we can make this pathway. And I said, okay, but now this is interesting because the aluminum's kind of a spectator here. Do we have to do it with aluminum? And I did that thing that professors do. I said, hey, I have an idea that took me less than 1/10 of a second, and it's going to take you 5 months of your life to do. She said, fine. So she did those calculations. And so if we do a reaction pathway with magnesium and oxygen, aluminum and hydrogen in some arrangement, we get product of ALOH and we lose the magnesium. It's also true for silicon, although we can't start with ALH, we have to start with ALO and SiH. Similarly with phosphorus, and then with sulfur, we actually can use either one of these if we go through the right pathway. So we can make ALOH from any hydride as long as we have. Okay. I'm having way too much fun, but y'all need to get out of here before midnight tonight. So let's go back to our minimum energy diagram, or our minimum energy gulf. We've talked a lot about aluminum and oxygen. What about silicon and oxygen? Maybe silicon and nitrogen. So I had Allie do some calculations on these structures to see if we could form them. And we get a big, we don't get a huge dipole moment. We get some vibrational frequencies with some intensities. But I'd like to pause here. Y'all have gotten to know me over the past half hour. You know I like really, really terrible jokes. Anybody know what the name of this molecule is?
Silanol?
Silanol.
Yeah, Silanol.
So it's Silanol, but you don't want to take this if you're pregnant. Okay, so that was a. Okay, so we have Silanol, but believe it or not, Silanol has never been uniquely synthesized and characterized in the infrared, which I found to be surprising. It's methanol, but with a silicon. Of course, you have to start from silane, which I hear is pretty insane and highly explosive. But we were able to calculate some infrared frequencies as well as a dipole moment, and we get some notable intensities. Okay, that was kind of a side trip, but let's go back to our chemical reactions. Can we do some chemistry? Can we take small molecules, react them with water, and form bigger clusters? So my student Athena, who recently graduated, is now doing a postdoc with the Corps of Engineers, said, what if we start with SiO and water, and the reaction pathway eventually goes through various processes. We add another SiO. One of the problems with this is that we have to have vibrational radiative association for this to work, but I have a different mechanism I'll show you later. Basically, the point is we can add SiO in some cases. We have a lot of chemistry that happens, a lot more chemistry, but then it eventually makes this really cool product all the way on the right. It's Si2 trimer. SiO2 trimer. SiO2. What's SiO2? Silicon dioxide. What's the common name for silicon dioxide?
Silica.
Silica, or we're here in Miami.
Sand.
Sand. Yeah. So it's the major component of sand. So we're able to make a cluster of this just starting from small molecules in the gas phase. All right. Keep going. What about magnesium? It's become slightly more important in a minute. Magnesium and oxygen, if we take MgH and react it with water, it has the same motif that we got with aluminum. It eventually goes on to make Mg2O2, MgO2. That's actually a mineral as well. That's the mineral periclate. We're making some more minerals. All right. So we've made corundum, rubies. We've made sand. We've made periclase. Not to be confused with Pericles, who is somebody else. What happens if we combine the magnesiums and the aluminums, maybe the silicons together? So Athena did this work. I'll spend a little bit more time on this. So we have MgH. MgH2, probably not going to form. MgH has been observed in the sun. MgH has been observed in Jupiter. I have the suspicion that most small atoms are going to form hydrides through radiative association when they're ejected from their parent stars, because there's just so much hydrogen, and there's so many electrons flying by. So if we have MgH, even though it hasn't been found in the interstellar medium, we know it exists in astronomical environments. We react it with water, which is ubiquitous. It goes through the same motif. It makes MgOH. What can we do with MgOH? If we react that with another MgH, we form this really insane little molecule. This is MgO2. So it's a magnesium in the middle with 2 oxygens on either side. It's shockingly stable. Now, you wouldn't be able to make this in the gas phase under terrestrial conditions, but it doesn't just react with the first thing that comes along. It is kind of potent, but its electronic structure is very stable. You take an electron away or you add one to it and it goes crazy. But we're able to get through the same pathway where we make MgOH, we add another MgH, submerge barriers all the way through, and we make this fun little intermediate. Once we make that guy, we can hit it with SiO. And we have a downhill reaction once more, net downhill reaction. We lose a magnesium. A lot more chemistry happens. There's a bunch of stuff, you don't have to worry yourself with it too much, but just know that we can add a water to this. Our transition states are mostly submerged. This first one here is 1 kcal per mole above. So this isn't going to happen in deep space, but it may happen in somewhat warmer environments. To get 1% of your material over that hill, that 1.2 kcal per mole hill, only requires about 70 Kelvin, which is well within most of what we have here available in the solar system. And we eventually create MgSiO3. There's a pathway where we can add another magnesium to it and make Mg2SiO4. And Mg2SiO4 is the major component of the mineral olivine. And it's this beautiful green rock. Olivine is comprised of Mg2SiO4 and Fe2SiO4. Remember the Fe2SiO4 that's going to come back in a minute. It's mostly magnesium. It's like 90% magnesium, but there is iron that adds into it. Speaking of beaches, I got these. Don't tell the National Park Service. I got these from Hawaii. If you've ever been there, there's a thing called the Green Sand Beach on the Big Island in Hawaii Volcanoes National Park. The sand is green because the magma that's coming out of the volcano is mostly olivine. Olivine is some ridiculous, I forget, I used to know off the top of my head, it's like 50-something% of the Earth's mantle is comprised of olivine. So most of the mantle is comprised of this mineral. And what I have just showed you is a reaction pathway that starts with 2 magnesium hydrides, and SiO, 3 magnesium hydrides, and SiO, and 4 waters. Gas phase molecules aggregate together, and they can make clusters. That can then go on to make these guys. I'm gonna skip this part. It's fun. Great. All right, fine. Good. Yep, we found these guys. Rebecca also did calcium. It does similar things. I got 2 short stories that I would like to tell here to finish up. What about nitrogen? I've been telling you about oxygen. What about nitrogen? I had a student that was really, really interested in the nitrogen chemistry of this. So if we do the same reaction, all we've done is replace the water with the nitrogen. Guess what? Oh, yeah, this was Zach. We made a new friend one time. So we form this dative bonded intermediate. We have ALH3 and NH3. It's a cool structure. The lone pair of the nitrogen is donating in there. For those of you that are into material science, you replace the aluminum with boron, you make ammonia borane. And ammonia borane can have the same functionality as ethylene does. And so you can actually make buckyballs out of this. But when it does that H2, it hits this transition state that's above our reaction materials, which was a little surprising and a little disappointing, because this means that this is not going to happen in deep space. You still need some energy to get over that barrier. We did, yeah, let me get through this part. Running out of time. I have way too much fun talking about these things. But here's the initial reaction again. Zach was able to carry this out to its natural conclusion. And he eventually makes this thing that's Al2 into H. This is not a mineral per se, but molecules containing but molecules containing one aluminum and one nitrogen, and these big clusters have been found in comets and meteorites. We know that they exist in these environments. I showed you this diagram. There's no nitrogen. Why do we care about nitrogen though? Okay, we're almost done. So tell you what everybody do, let's take in a nice big breath and breathe it out. What was most of what you breathed in?
Nitrogen.
Yes, you didn't fall into my trap. Usually I say this, people are like, oxygen. Guess what? It's only 79%. 79% of that was nitrogen. Yes, it's nitrogen. Nitrogen's in the atmosphere. How did we get the nitrogen here? Maybe they were in these rocky materials replacing the oxygen with the nitrogen, and that's what deposited here on the Earth. We were also able to show that we didn't need NH3. We can do this, or ALH3, we can do this with just ALH. The barrier is higher. My student Jacob did this. We eventually make the same thing if we start from the same material. But we have these things called protoplanetary disks. Love to talk to you about them. Basically, this is a baby solar system. The one question that I'll ask, so we have a central star, then we have these rings. Anybody know what causes those rings? I'm not going to promise to do a cartwheel. Somebody's going to know. So we have the dust. We have the dust all throughout here, and then we have holes in the dust.
Gravity.
Gravity of what kind? P and then planet.
Planetary.
Yes. Planets cause those rings. Planets cause those rings. This was theorized for a long time. Alma was able to show this. So we have these rings, and in those regions, the dust, where the dust forms, where it aggregates, we have a region right at 1,000 Kelvin where we know the dust begins to form. At 1,000 Kelvin, you get 2% of that reaction to go over the previous reaction to go over the barrier. And so we have physical regions where we can create these things. All right, last thing. You've seen a version of this before. You've seen a version of this before. But here's what I want to highlight. Let's look at it backwards. So if we start from sand and we add hydrogen, it's got to go uphill. But if we can go uphill, the hydrogen adds onto this oxygen and this oxygen, transforms over, and then we make water. And we do it again. And we do it again. We're making water out of sand, pulling the oxygen out of it. What do we need to do this? Well, we need hydrogen and we need energy. Okay? If we take each of the hills necessary to get from one to the next, all the way back to making 4 water molecules out of this, the energy we need to climb each of those hills are the color bands that we have here. And this is the black body spectrum of the sun. Sunlight can do this. What about olivine? Showed it for sand. Olivine's more common than silica. Olivine's more common than sand. A simplified version of the reaction that I showed you, where we start from instatite, or start from MgSiO3. We have that big hill that we have to climb. We translate that, that's still only 230 nanometers. That's within sunlight. And folks, this isn't theory. This is real. This paper came out last year. Remember I told you there were 2 end members of olivine. One was fosterite, which is Mg2SiO3, Mg2SiO4. The other is phthalate, which is Fe2SiO4. This group at Arizona State took a phthalate sample, put it in the middle, put it in an anvil, heated it up, ran hydrogen gas over it. Suddenly, the phthalate was broken down. They had 2 pictures of it. And you know what they found on the other side when they ran water over this and heated it up? When they ran hydrogen over this and heated it up? They made water. I sent the guy an email and said, oh, this is fantastic. I'm so excited about your research. We've been talking about the theory of this for a long time. He sends me a note back, says, thanks. Leave it to the engineers. They don't care how it works. They just want it to work. But for me, this was really validating because as a theoretical chemist, we spend all of our time calculating things that may or may not be real. But here we have validation that this is real. Why is this important? Most of the regolith on the moon is comprised of these same materials. So if we can take material from the moon, the regolith itself, already a powder, if we can take that, run hydrogen across it, expose it to sunlight, and pull the material out, we make water. We make it on the moon. We don't have to fight with China over the South Pole, and we can have permanent stuff. So with that, I hope I gave you a little entertainment. I hope that I convinced you that I am twice as nuts as you originally thought I was. I'd like to thank all of my students. And this is a shameless bit of self-promotion. If you happen to notice, these two NASA grants, which I've just had funded, have consecutive numbers because we were, my friend Vince and I got grants funded in the same grant program at the same time by the same group. One was on PHs, one was on this. And I am so excited about this because now this means that NASA wants me to keep doing this work for at least 3 more years. So we talked about, so I wrote a book. Sabrina also said that I like to climb things. This is a picture of me at the highest point in Florida. 345 feet. No offense, the high points of Florida suck.
Yes.
So, I'll show you one of me being more awesome on top of a mountain somewhere. Thank you so much for your time.